Okay, hi everyone. For our second lecture, so this is week 1, part 2, we're going to be talking about the birth and death of oceans as well as the ocean floor. So to start, today we're going to sort of pick up where we left off from Tuesday's lecture, talking about plate boundary types. So I introduced them briefly at the end of Tuesday. We're going to go into them in some detail today, including the Wilson cycle, so how we actually form, grow, and then remove an ocean from the surface of the Earth. Then we're going to go over bathymetry and the ocean floor. So plate boundary types in the Wilson cycle is sort of the first part of our lecture. It goes together, and then we will get into the ocean floor and the different components and pieces of the floor. So the goal for the first part of this lecture, you should be able to explain the Wilson cycle and the different stages within the Wilson cycle. Also, you should be able to draw the different features that occur due to divergent, convergent, or transform boundaries, as well as explain hotspot activity and how hotspots create island chains, and understand the direction of motion of the plate above the hotspot. So to start, I have this map of earthquakes. So each green dot shows an earthquake since 1898 by magnitude. So the larger dots are the stronger earthquakes. You will notice there are some very clear patterns. This area is actually called the Ring of Fire all around this Pacific Ocean here. This is Hawaii. Here's North America. This area is called the Ring of Fire due to the tremendous amount of earthquake and also volcanic activity going on around at those plate boundaries. So again, here are the volcanoes. You'll notice that this Ring of Fire around the Pacific Ocean matches quite well with many of the volcanoes in, again, what we call that Ring of Fire. Which matches, of course, quite well with our plate boundaries. So we can see there's clearly a pattern of volcanism and seismic activity where we have tectonic plate boundaries. So to start, if you remember, our lithosphere floats on top of our asthenosphere. So the crust is floating on top of that asthenosphere, on top of that malleable mantle material. And there are two types of crust, oceanic and continental. So in these diagrams, you can see this darker gray thin layer under the water is the oceanic crust. The thicker beige above sea level lithosphere is the continental crust. So I am going to go through each of these three boundary types and explain exactly what's happening. So that goes along well with the Wilson cycle, which is known as the cycle of ocean life. So the life of an ocean. So it starts with the birth of an ocean, so the actual formation of an ocean on Earth. And then the ocean grows, the life of the ocean, and then the death of the ocean is where the ocean is removed or closed up. So we're going to go through each of those steps involving the plate tectonics that causes this Wilson cycle. So we start with a divergent boundary. So divergent boundary where the plates are moving apart. So here are two continental crust plates. Here is a spreading center, like we talked about, and these two plates are moving outward. So there's new mantle material coming up from the mantle and pushing these plates away. So the new mantle material that comes up from this spreading center is going to be oceanic crust. So mantle material that comes to our surface is always going to be oceanic crust, which means it is much thinner, it is much more dense, so it's going to sink lower. It's going to be much lower on that asthenosphere than our continental crust, so water will start to accumulate in this region, starting probably as a sea, and then as the spreading center continues to push these apart, we will eventually have an ocean with our mid-ocean ridge in between. So this is a divergent boundary pushing these plates apart. New crust inside is formed from this mantle material coming up from this magma plume there. So that is the very start of the Wilson cycle, so sort of how an ocean is born, how we actually form an ocean, due to a divergent boundary, so a boundary pushing the continental crust apart. So as you can see, this is an example here of a divergent boundary that has started to create an ocean. It is very, very, very slowly spreading the Red Sea wider and wider and wider apart. So here is another diagram of our divergent boundary. So at our divergent boundary is where we find our mid-ocean ridges. This is also what we call a spreading center, because it is spreading these plates apart, creating new rock, creating new oceanic crust, creating new ocean floor there as that magma cools. Excuse me, it would be lava, as that lava cools on the surface. So the largest, the main mid-ocean ridge that we hear about is in the Atlantic Ocean, so pushing Africa further from South America, growing our Atlantic Ocean. The newest rock is right along the ridge because it's brand new. It just came up from the magma chamber beneath. Brand new rock right at the ridge. As the rock ages, it is moved further and further and further from the ridge. So the oldest rock will be as far away from the ridge as you can get. So I do have links throughout the PowerPoint to some graphics. If you want to check out these websites, you're more than welcome to. They're little videos that show the plate motion, show the plate motion as a cartoon video. So those can be helpful if you want to check those out. So if we look at our crust age, so this is age of the crust, you will notice that at age 0, the red color is right along all of those mid-ocean ridges. So the youngest crust is going to be what has just formed right at that mid-ocean ridge, increasing in age as you move away from the ridge. So here are some examples of divergent boundaries. So we have one quite close to us, the Gulf between Baja, California, and the rest of Mexico there. This is slowly spreading apart. So that would be this portion of our Wilson cycle, as after the continents have spread apart, allowing for that oceanic crust to form. Water will fill in, and the oceans will continue getting larger and larger. So the first question on your lecture quiz is, which letter shows the location of the oldest oceanic crust? Let's think about that for a second. Which letter shows the location of the oldest oceanic crust? So you should be thinking, okay, I know the youngest crust is right on that mid-ocean ridge. So of course it would not be C or D right on the ridge. We're talking about oceanic crust, so it's not E because that's on the continent. So you're going to want to look for the letter that is furthest away from the spreading center. So the answer would be A here. A, which is furthest away from this spreading center, from any spreading center, is going to be the oldest of the options here. So that is our divergent boundary, where we have plates moving apart. We have new mantle material, asthenosphere material coming up to the surface, creating new oceanic crust. That is new ocean seafloor that, as it ages, is going to be pushed further and further and further along by the new mantle material coming up to the surface, cooling and then spreading. So the divergent boundary or mid-ocean ridge or spreading center here. This is how you grow and create an ocean. So next we will go over convergent boundaries. So convergent boundaries are where plates are moving towards each other. And there's a couple types. We're going to go through all of the options. So convergent boundaries, this is where two plates are moving towards each other. And if you imagine these are massive tectonic plates moving towards each other, something's got to happen when they collide. So you can either have a convergent boundary made of oceanic to oceanic crust, meaning both plates that are converging are oceanic crust, so this gray here, shown here underwater. Or you can have oceanic to continental crust. So here we have oceanic lithosphere and continental lithosphere coming together at this divergent boundary. So first, let's take a look at oceanic to oceanic continental boundary. It's oceanic to oceanic convergent boundary. Excuse me, that should say convergent. This is going to create what we call subduction. Subduction is when one plate sinks beneath the other one into the asthenosphere. So that is exactly what this diagram is showing here. Here we have one oceanic plate. It is moving in this direction. We also have this oceanic plate moving in this direction towards each other. Where they meet, eventually one is going to subduct underneath. So the oceanic crust, remember, is quite dense. So it is actually dense enough that it can sink down into the asthenosphere. So the most dense crust is going to sink down into the asthenosphere. What that means is the oldest crust will actually sink down, because as the continental crust ages, it's going to become more and more dense. So the older crust is always going to be the crust to subduct in an oceanic to oceanic convergent boundary. So as this crust is subducting, it is subducting down into the asthenosphere. That is quite hot. What happens is some of that crust actually starts to melt. So there's some chemistry that goes on at this point, which we are not going to focus on too much for this class. I'm happy to talk about it more if you guys are interested. Shoot me an email, or in office hours we can go over it. But what you should remember is that this oceanic crust is sinking down. It's going to increase in pressure because now it's underneath all of this other material, and also it's going to heat up. So this material is going to melt, and since it's melting, that means it is a liquid. Liquid is going to be much less dense than the solid material around it. So it's going to rise up through the overriding plate. So this plate subducts down into the asthenosphere. Once it gets deep enough, it's going to start melting. Now that liquid magma, that melted rock, is going to rise up towards the surface. It's actually going to rise all the way up to the surface. When magma reaches the surface, it creates a volcano. So that is how we create volcanic island arcs. So that is a line of volcanoes that are islands above and on the overriding plate. So the subducting plate is the one that melts. That melted material rises up and creates volcanoes. So sometimes these volcanoes are quite large, and they can actually be above the sea level, so they'll create islands. Or sometimes they aren't quite large enough, so they will just be completely underwater. So whenever you see a volcanic island arc, you know that you are near a subduction zone. You know it is an ocean to ocean, oceanic to oceanic convergent boundary. Another key factor is a trench. So when you are subducting downward, there's a little bit of friction. So the subduction always creates a trench right where the plates meet, a trench being a very deep part of the ocean floor. So where you see a trench next to a line of islands, you know that there is subduction going on, and it is oceanic to oceanic subduction. So here are some examples. So you'll notice along this line of volcanic islands here, the volcanic island arc, you also see a very, very dark color there, signifying a very, very deep part of the ocean. So there is a trench right next to a line of islands. You know that there is subduction occurring. So the same here, There's actually quite a few. Very, very, very deep trenches right next to a line of islands. So here is another diagram. I have lots of diagrams to show. You will see the trench. Right next to the trench, you see the volcanic island arc. So as this plate is subducting down, it starts to melt, that liquid magma rises up, creating volcanoes. So the second type of convergent boundary is oceanic to continental. So this is very, very similar. However, instead of two oceanic plates converging, we have one of each. So if you remember, the oceanic crust is going to be always much more dense than the continental crust. So the very dense material, the oceanic crust, is going to subduct beneath the continental crust. Always, always, always. It is always the oceanic crust that subducts beneath the continental crust. So you'll notice, again, we have subduction of our oceanic crust underneath that continental crust, again creating a trench. So creating a very deep part of the ocean floor, right where our subduction is occurring. The subduction pulls this oceanic crust down into the asthenosphere. We have melting. That melted magma then rises up, creating volcanoes. However, since in this case, the magma rising up is going through continental crust, we are not creating islands, we're just creating mountains. So creating a mountain chain. So instead of calling this a volcanic island arc, we call it a continental volcanic arc because it's very similar. It is still going to be a line of volcanic islands, a line of volcanic mountains. However, they're not islands because they're surrounded by land. So where you see a trench offshore quite close to a line of volcanic islands, you know that there must have been subduction going on to create the trench, which then also created that line of mountains. So here are some examples. In the Andes, you can see this very, very, very deep trench, that very dark black line. Then there is a huge mountain range all the way along that continent, as well as the Cascades. So the Cascades Mountains, that mountain range was created by subduction. So this plate is subducting, and then it, at the trench, subducts underneath the continent. As it subducts underneath, that material melts and then rises up through the continent, creating this very large mountain range. So again, I just have many diagrams to make sure that you have many different ways of seeing what's going on. So the lithosphere, our oceanic crust, sinks down, subducts underneath our continental crust, because remember, the oceanic crust is much more dense, so it's going to sink beneath the continental crust. That material is going to be so deep down in the asthenosphere that it will start to melt. It will rise up through the overriding plate, creating volcanic mountains. So that is how you can remove an ocean. So for example, this oceanic plate is going to slowly be sort of swallowed up by this subduction zone. So where you see an ocean closing up in our Wilson cycle, so this is almost the death or the removal of the ocean, as this oceanic crust continues to sink, continues to subduct underneath our continent. It's going to pull whatever is on the other side of it, eventually another continent, closer and closer and closer and closer, because it's just going to keep subducting. That oceanic crust is always going to be more dense than the continental crust. It's going to continue subducting, moving closer and closer and closer and closer to the continental crust there. So that brings us to actually the third type of convergent boundary, which we call continental collision. So it's actually very different than the other two types of convergent boundaries. Here is where we have two continental crusts coming together. So they are coming towards each other. It is continental convergence, moving towards each other. However, if you remember the last two examples, we had dense oceanic crust subducting. Continental crust is never dense enough to actually subduct into the Earth. So continental crust is so light, it is not at all dense enough to subduct down into the mantle. What happens is we have real collision. So these two pieces of continental crust smash into each other and just continue moving towards each other, continue crushing material in between, creating the largest mountain ranges that we have on Earth. So this is exactly what happened as India moved up towards the rest of Asia. It collided, so we ended up with two continental plates colliding, creating the unbelievable mountains of the Himalayas. So that is what we call the death of an ocean, so the suturing of the ocean. So as this continental crust is carried towards the other continental crust by this subduction, eventually this continental crust will smash into the other continental crust. Neither of them can sink down, neither of them can subduct. So if you imagine you're at the beach and you take your hands on top of the sand and you push two piles of sand together, the sand is going to go up. The sand's going to go up from in between your hands and then all over you. That's exactly what happens with on a much slower scale, what happens with two continental collisions. So two continental crusts coming together, it's going to smash into each other. That material cannot go down, so it has to go up. I want to show you the video of the continental to continental collision. It's not a video, it's a cartoon video. So here you can see we're using the Himalayas as an example. So the Indian plate was moving up towards the Eurasian plate. It still is, actually. So the oceanic lithosphere is subducting down. This is first an oceanic to continental convergent boundary. We have creating some mountains here from that subduction. It then becomes a continental to continental collision. So the subduction stops because this continental crust cannot sink down. So what happens is this material just continues growing upwards, creating the highest peaks we have on Earth. So the Himalayas are actually still growing in size. So they are very, very, very slowly. This happens on millions of years. But they are actually still getting taller. So let's go back to this. So that is our convergent boundary. So where we have two boundaries moving towards each other. This is how we shrink an ocean. So there are continental to continental collisions, oceanic to continental convergent boundaries, what is shown here. You can also have oceanic to oceanic convergent boundaries. So the next type of boundary, the last of the three, is called a transform boundary. So this is different. We do not have motion towards or away. The plates are merely sliding past each other. So this here is the transform boundary, where the plates are sliding past each other. So transform boundaries are generally always associated or nearby mid-ocean ridges or spreading centers. That is because spreading centers they're not perfectly straight lines. They can become offset depending on the speed. The production of new crust is not the same all over the Earth. So sometimes you end up with a little bit of offset, meaning that you're going to have this piece of crust moving, in this case, to the left, or you have this piece of crust moving to the right. fueled by that mid-ocean ridge, so you end up with these pieces sliding against each other. That would be a transform fault. So they are sliding past each other. So an example is right here. You see this offset in our mid-ocean ridge. So right here, you're going to have a lot of motion sliding past each other. So again, you can see exactly what I'm talking about with the offsets, where that mid-ocean ridge is not a perfect straight line. There's actually quite a bit of jumping around that they have there. So I will show you. This is an example of a transform boundary that is quite close to us if you're at UCI, the San Andreas Fault. So here we're looking at the Pacific Plate and the North American Plate. They're moving in the same direction, but they're moving at different speeds. So technically, we down here in Orange County are on our way up to San Francisco without even realizing. So that causes quite a bit of earthquakes along this fault as our plate moves much faster up towards the north. So again, all these videos that I show are linked in the slides, so if you want to come back to them on your own time, you can check them out. That's a really cool site there. So a lot of diagrams will show that the transform boundary is where two plates are moving in opposite directions. That's not the only case. It can be like what I just showed with the San Andreas, where the plates are moving in the same direction, but at different speeds. So they're still sliding against each other along that boundary. So that is our last plate boundary, the transform boundary there. This is going to be the boundary that will shift things on Earth. So it's not creating or destroying, it's just moving things around. So for the next question, think about continental crust and the fact that continental crust cannot ever be subducted back into the mantle. It is not dense enough. So what do you think has happened to the area of our continents through time? If continental crust can never be subducted, what do you think has happened? If you're thinking that the area of our continents must have increased because it can't have decreased, you're exactly right. So new volcanic islands, for example, have eventually added onto our continents. Our continents have just, I would say very slowly, but have continuously increased in area. So the area of continents on Earth has been slowly increasing, so we cannot get rid of continental crust. So that summarizes the Wilson cycle, this slide here. We have the birth of our ocean with the opening up of the ocean of divergent boundaries. So we have this continental crust spreading apart, creating new creating new oceanic crust from this mid-ocean ridge. This will eventually fill with water, creating a sea, which will, as this continues to diverge, create an ocean. Here we have our mature ocean. We can say this is the life of the ocean. And then eventually, what ends up happening is this oceanic crust is going to start subducting. So if we are getting rid of the ocean, or talking about the death of the ocean, as we say, that is when the oceanic crust is subducting underneath our continental crust, to the point where we actually run out of oceanic crust. So remember, that means this continent is actually creating really large mountains at this point from this subduction, but eventually this continental crust will smash into the other piece of continental crust in a very violent continental to continental collision, creating some of the largest mountains we have on Earth. Actually creating all of the largest mountains that we have on Earth. The Himalayas are really the best example. So another piece of tectonics that we have to talk about is the instance where we have volcanic activity and earthquake activity in the middle of an oceanic plate. In the middle of a tectonic plate. So generally, volcanoes and earthquakes are always associated with some kind of tectonic boundary. So any one of those types of boundaries creates earthquakes. Anytime you have tectonic plates moving against each other, there's a lot of friction. There's going to be a lot of earthquakes. All types of subduction will create volcanic activity. However, transform boundaries do not create any volcanic activity. There's no melting going on there. There are a few places on Earth, however, where we have volcanoes, volcanic activity, and earthquakes, but it's in the middle of a plate. So, for example, Hawaii is in the middle of what we call the Pacific Plate, and yet it is a chain of volcanic islands. This is because Hawaii is directly over a hotspot, or a mantle plume. So a hotspot is where we have a plume of liquid mantle material rising up through the crust to the surface of the Earth. So what happens is this is a little escape of heat that is always in the same place. So this mantle plume never moves. However, the Hawaiian island chain is called a Hawaiian island chain because it is in fact a chain or a line of islands. That's because the Pacific Plate has been moving over or on top of the hotspot. So the hotspot is always constant. It is always in the same exact spot, but the plate on top is moving over it, meaning it's going to carry the older islands away from that hotspot, allowing for the creation of new islands. So that is exactly how Hawaii was formed. So here's another example. You'll see that this Pacific Plate is moving away from the hotspot. The hotspot, the mantle plume, is always there. So as this plate moves away, it's carrying the older islands away. So I have a video of this one too that I want to show. Here we go. So here is the hotspot rising up through the crust. So as the crust moves on top of the hotspot, new islands are formed. Also, as this is going, this is millions of years, so the older islands get smaller. You'll notice that the biggest islands are the newer islands. They're getting smaller because of erosion. I should mention that. They're just slowly being eroded away. So when we look at the ocean floor around Hawaii, we notice that, although you may be familiar with the first few islands of Hawaii, it is actually a massive underwater mountain chain caused by the hotspot that is still in this location, but it's just that this Pacific Plate has been moving over the hotspot. You can actually see exactly where this plate started turning. So the Hawaiian Islands, as well as other hotspot islands, are really great for calculating the speed of the plate motion. So you can say, well, 3 million years ago this island was formed, 2 million years ago the next island was formed. These are theoretical numbers. Then you can calculate how fast the plate was actually moving. So Hawaiian hotspots, all hotspots, but mostly Hawaii, because it's so active, is really like a gold mine to geologists. So here is a question for you. On this picture, the triangle shows the active volcanic island. So this triangle is showing the volcanic island created by a hotspot. The circles, this way, are the older volcanic islands that are no longer active. So they're no longer active volcanoes. They used to be above this hotspot. So looking at this volcanic island chain, which direction is the tectonic plate moving? So I'll give you a second to think about which direction do you think the tectonic plate is moving on top of that hotspot. So to think about this, you want to recognize that the magma chamber, the magma plume, that hotspot is located right here, which means this oldest island used to be right here. The plate has then slowly been carrying it away in this direction, meaning the plate is moving to the southeast. So the answer here should be A, to the southeast. The plate is slowly being carried away from that hotspot towards the southeast. So the next thing to go over are coral reefs. Coral reefs are created around often these volcanic islands. You may have heard of them. Many of them are in danger right now due to ocean acidification and warming of the ocean. We're going to get into that aspect in week 5 of this class at the end. But for now, let's just talk about the formation of coral reefs. So there are sort of 3 steps. First, a fringing reef is formed right along the edge of the volcanic island. Eventually, that volcanic island will be eroded away. When it is partially eroded away, that reef is going to continue growing. So the reef becomes what we call a barrier reef, where in between the island, which is now much smaller, and the reef, we have very slow-moving water because it's protected by the reef itself, so we call that a lagoon. So in between would be lagoon water. And then once that island is completely eroded away, we have just the reef left over in the end, an atoll here. So here are some actual examples. This is Bora Bora in the Pacific Ocean. This is in French Polynesia. And then here is another figure. So our nice erupting volcano here, the coral reef, the fringing reef, is growing right along the edge of the island. The island, however, is much more easily eroded than the reef is, so that island is going to start being eroded away. That island will slowly disappear, but the reef will stay. So here we have a barrier reef where we have the partially eroded island in the middle, surrounded by lagoon, and then our barrier reef. And eventually, all that's left is the lagoon because the entire island has been eroded. So here is a map of all of the hotspots on Earth. You'll notice that they don't necessarily match up with our map of tectonic plates. That is because the Hawaiian Islands don't have anything to do with plate boundaries. Well, the Hawaiian Islands, yes, but I meant to say hotspots on Earth. Hotspots have nothing to do with plate boundaries. They are completely independent, and they're not always in the ocean. So, for example, Yellowstone is a hotspot. So Yellowstone, beneath Yellowstone, is a magma plume, a magma chamber. If you've seen the geysers. There's a lot of heat being released. That is due to the magmatic activity of that hotspot underneath the North American continent there. So this is a map of what the world will look like in 50 million years. So geologists have been able to predict what the world will look like based on our plate boundaries and how the plates are moving and will move for the next 50 years. So you'll notice that you can still sort of see the outline of our continents and countries. That's because 50 million years is pretty short for geologic terms. So there isn't a huge amount of motion. Plate tectonics happens over a very, very, very long time scale. It's incredibly slow, but it is very powerful, shifting our oceans and our continents around all over the surface of the Earth. So this is the end of part 1 of this lecture. So that is on plate tectonics and plate boundaries. So the 3 boundary types. I hope you're feeling more comfortable with all 3 boundary types: divergent, convergent, and transform. So from here, we will start talking about the ocean floor, what it looks like, the different features, and how we know. So some of the outcomes today, we're going to talk first about hazards, so geologic hazards that we see with plate boundaries. Then we will get into maps of the ocean floor, how we know anything about the ocean floor. And then you'll be able to draw and label and identify all the different major features on the ocean floor. So those are considered continental margins, deep ocean basins, and also mid-ocean ridges, which you should now be very familiar with. And then at the very end, I'm going to go over drawing cross sections because you will be doing that in your next discussion activity. So Tuesday of week 2, that discussion activity will be drawing cross sections of the Earth with your groups. So earthquakes are a large geologic hazard. There can be some serious damage with earthquakes on Earth. Here we have a map that shows the depth of earthquakes. So shallow earthquakes are in blue. Yellow shows intermediate earthquakes, and red shows deep earthquakes. So you'll notice that along our mid-ocean ridges, where we have our spreading centers, we have a lot of shallow earthquakes. So anytime you have a plate boundary, anytime there's continental plates rubbing against each other, moving against each other, there's a lot of friction, there's going to be earthquakes. But with divergent boundaries, there's really no vertical motion, they're just separating. So we have a lot of shallow earthquakes, meaning that the earthquakes are on the surface of the Earth. They're not very deep down. However, where we have subduction zones, which is around this ring of fire, if you remember, that is where you're going to have deep earthquakes, because earthquakes will occur as that oceanic plate is subducting. So if you remember the subduction, the oceanic plate sinking down into the center of the Earth, that whole entire time as it's sinking down, it is rubbing against other rock. So as it is sinking down into the mantle, it's still going to be creating earthquakes, meaning that at these subduction zones, you can have shallow, intermediate, or middle, and deep earthquakes. So if you think about the shape of the Tonga Trench, which is right here, based on the map of the earthquakes, what do you think the shape of this trench would look like? So think about subduction and think about the direction of subduction at this trench based on the earthquakes. So which of these drawings here do you think most accurately shows the shape of the plate boundary at the Tonga Trench? So the trick here is to use the earthquakes to answer the question. So we have deep earthquakes on the western side of this trench, shallow earthquakes on the eastern side of this trench. So the red versus the blue. What that tells us is there must be motion deep under the surface of the Earth on the western side. So we know that there's a trench, so it can't be a mid-ocean ridge. This is showing a little mountain range. That would be a mid-ocean ridge. It can't be that. But we know that the deep part is on the western side. So the answer here must be B, where you have oceanic crust sinking down, and to the west, we have that deep motion. So as this crust is sinking down to the west, all along here, there's going to be friction of this subducting plate sliding down into the mantle material. So we're going to have a lot of deep earthquakes here on the west, where you'd have a lot of shallow earthquakes here on the east. So towards the east, you have a lot of shallow earthquakes where the two plates are meeting right along that trench. And then as you move to the west, the earthquakes are going to get deeper in the center of the earth as that plate is subducting downward. So subduction not only creates volcanoes and earthquakes, but also tsunamis. So volcanoes, earthquakes, and tsunamis, all from subduction zones. So here is a video to show you how tsunamis are formed. So tsunamis are a massive movement of water. So in order to move water, in order to move that amount of water at that speed, there has to be a large shift in the bottom of the seafloor. So I'll show this video and then continue explaining. So this plate is subducting underneath. And there is our big tsunami. Oops. The wave then moves outwards in a circle. So what's happening is I'll show you one more time. This plate will subduct underneath. As it's subducting, it's creating that trench. So that really deep trench that we talked about, that's always associated with subduction. Because the overriding plate is going to get pulled a little bit. Remember, there's a lot of friction. This is not a smooth process. This subducting plate is going to be subducting down. The overriding plate will get pinched a little bit downward to the point where it can't handle that pressure. It's going to snap back up. That snap of vertical motion of the plate is going to send a lot of water straight upwards. That is the start of the tsunami wave. So that tsunami wave will then emanate outwards in a circle pattern. So let's watch one more time. We have that subduction. Here we're building up pressure from friction. It's going to snap and displacing all of that water, sending it directly vertically up, which will then spread outwards as a huge wave. So the tsunami wave, if you are out to sea on a tsunami wave, you might not even experience it. You might not even know. The water would just maybe go up and down because the wave is so big. Where the tsunami becomes really dangerous is when it reaches the shore. So when the shoreline comes into play, that is where you have the very, 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 very large waves being created from all of that extra water. So in week 3, we're going to go over waves and coastlines. Week 3. So there we'll get more into how waves work. So here I just want you to remember that tsunamis are only created at boundaries where there is vertical motion. So you have to have that vertical snapping at that subduction zone to create a tsunami. So tsunamis are incredibly dangerous. They move incredibly quickly. And they can be incredibly tall because there's so much water moving so quickly all at once. The wave can be 10 to 15 meters high or more. And it's not just one wave. So there's not just one tsunami wave. It will be a whole set of multiple very large waves. So for example, some of you might remember in 2004, there was a absolutely horrible tsunami in the Indian Ocean caused by a subduction zone there. There was a magnitude 9 earthquake, and the tsunami wiped out quite a bit of land. You can see this picture. This is before and after. So before here, we see nice green towns. After the tsunami wave completely destroyed this region. This was a horrible, horrible, horrible natural disaster, displacing almost 2 million people just from this one storm, this one tsunami. So they can be incredibly dangerous. There was another in 2011, so this was again a 9.0 earthquake caused by a subduction zone. So here you can see the trench, deep, deep trench. You can see the line of islands, so we know that there's a subduction zone happening here. So this again was a huge, devastating tsunami that the worst impact was in Japan, where of course it is the closest. It was almost up to $40 billion in damage, it's estimated. So tsunamis can be absolutely devastating because it is a massive amount of water. There often isn't much time for warning. However, places that are in regions that could potentially have tsunamis have definitely gotten better about warning systems to make sure that people know of earthquakes nearby that might have caused a tsunami or might be associated with a tsunami. So, should you be worried about a tsunami after an earthquake on the San Andreas Fault in Southern California? So here we are in Southern California. If there was a huge earthquake along that fault, would you have to be worried about a tsunami? The answer, lucky for us, is no. That's because the San Andreas Fault is a transform boundary. That means there's no vertical motion. Also, most of it is on land. So if you thought of that, that's a good point. But transform boundaries are just the boundaries moving side to side, moving past each other. So there's no vertical motion. For a tsunami to occur, there has to be vertical motion in order to displace that water, to send that water so high up. If you'd like to know more, I do have this link here. It's really good for learning about the dangers of earthquakes in this region specifically, where we are so close to a big fault. So here are some notes from, something that was written up after surviving a tsunami, is what he called it. A man named Brian Atwater wrote down these suggestions after himself surviving a tsunami. So listen to warnings. So listen when you hear that there is a warning, take it seriously. And it's not just one wave. So, and it's not guaranteed that the first wave is going to be the largest. So the first wave might be very devastating. You might think that it's over, but there are more to come. There are absolutely more to come, and they might be actually bigger than the first one. So the best advice is to get to high ground as quickly as possible. Climb something, climb a building or a tree, get up. So hopefully you will be above the water level. He also said, when in doubt, grab something that floats so that you can at least be in something like a boat. So the next part of lecture will be looking at the ocean floor. So what does the ocean floor look like, and how do we know? So the question is, how did we make a map like this? How do we know what the ocean floor looks like? Because you can't see it when you're looking at it from above. So the study of the ocean floor, we use the term bathymetry. Bathymetry is the distance from the surface of the ocean to the ocean floor. So it's essentially the topography of the bottom of the ocean. So this was originally done using sort of a measuring tape with a weight at the bottom, so a really long rope. You would drop it off the side of a boat and see how long the rope would go before it hit the ground and measure that distance. So this was the technique used for over 2,000 years until our technology got a little better. So we actually took a note from nature, and we used sonar similar to bats or dolphins. So dolphins and bats send out a noise. Once it hits something, those noise waves are going to be reflected back. So the dolphin can use the time or the delay to see how close things are to themselves. So if it took a very, very, very long time for the sound waves to hit something and for the echo to get back to them, they know there's nothing close by. Whatever it hit was very far away. If something's quite close, that means maybe the sound went out and back in quickly, so there was no delay. That means there's something right in front of them. So here I have a video, hopefully with sound. Yes. So that is what it sounds like to us, anyway, when the dolphins are sending out their sort of sonar sounds. So if you want to learn more about this process exactly, this is a really good YouTube link. It's just a couple of minutes. I'm not going to play it now for sake of time. This video here with the sound is this Vimeo link here. So it is pretty cool. So we sort of learned from the dolphins when we tried to study the bottom of the ocean. So what we do is we use echo soundings. So we use sonars very similarly to dolphins, and we send out pulses of energy downwards, and then we measure how long it takes to come back to determine, are we right above something very, very, very deep where it took a very long time for the pulse to come back, or are we in very shallow water where the pulse was sent out and came back very quickly. So these we call them multi-beams. They can either be attached to the bottom of a ship, like something like this, or sometimes they can actually be towed behind the ship. So this might be an instance where things are even deeper, or you're trying to cover more area. So these can be incredibly powerful, very, very good resolution, but super time consuming. Imagine trying to cover the entire oceans with a boat. We still do not have data like that. It is incredibly time consuming to get good data like this. So we can also use satellite observations. So it's not quite as precise as using the sonars on the boat, but it is great because we can get global coverage. So instead of having to drive our boat all the way around every single square inch of the ocean, we can just use satellites. So satellites actually use gravity. So really large features under the ground, so let's say a seamount or sort of a mountain underground is going to be very heavy, which means it's going to exert more gravity on the water around it. What that means is there's going to be a small bulge in the water surface above this very large feature because it's quite heavy. There's more land there. So satellites can actually measure the gravitational bulges across the surface of the ocean, and from there extrapolate where there are shallow features versus where there are deep features, where there is something large versus where there is not. So satellite bathymetry observations have actually become very, very precise in more recent times. So satellites have become a very reliable source of bathymetry data, still not to the resolution of ship data, but satellite data is great to use in places where we do not have ship data. So you can combine them together, sort of extrapolate out using the satellite data to fill in the gaps where we don't have the ship measured data. So here is a full bathymetric map of our oceans. So you can see the light blue color is more shallow. The darkest blue on our trenches, like we just learned about, is going to be the deepest parts of our ocean. Here is the deepest trench on Earth, the Mariana Trench. So, if you had to draw a little schematic of the Atlantic Ocean from west to east, what shape would it be in? So the top of each of these diagrams is sea level, going downwards into the deepest part of the ocean. Which shape do you think outlines the Atlantic Ocean? So if you remember, the Atlantic Ocean has a mid-ocean ridge running through the middle of it. If you remember about mid-ocean ridges are underwater mountain chains where we are creating new crust. It's that divergent boundary. We're creating new ocean crust. There's going to be a small mountain range there. So this shape here is the shape of the Atlantic Ocean. So if you were to walk, say, off the coast of the U.S., walk over to northern Africa, along the bottom of the ocean, you'd be going uphill for a very long time and then downhill. Of course, it is not a perfectly straight line. This is very, very smoothed out for this cartoon example. But that mid-ocean ridge in the middle is a mountain range. So we will have higher seafloor values, seafloor heights there in the center of our Atlantic Ocean. So this is an example of that cross-section that we saw here. So this is a much more detailed example. So here we have our continental margin. We're going to explain all of these in just a minute. If we walked from A to B along the bottom of the floor, the bottom of the ocean, we would walk down off the continent, across our ocean basin, across the ocean basin, until we got to our mid-ocean ridge, which would be up tall on top of our underwater mountain range here. We would then walk down the other side of that mid-ocean ridge until we hit the next continent. So our ocean floor is really made up of three different sort of sections, categories. The first being continental margins, the second deep ocean basins, and the third are mid-ocean ridges. So I'm going to go through what each of these three mean for the last part of this lecture today. So our continental margin, this is where continental crust shifts to oceanic crust. So it's the shallow area close to the continental shoreline. There are two types. There can either be passive margins or active margins. Active margins is where there is a plate boundary. So for example, here we have a trench, so we know that there is subduction going on because a trench is always created by subduction. Subduction means that this is a plate boundary. So this is a convergent plate boundary happening right here. This would be an active margin. So here we have a continental plate. This is a continental shelf, so this would be continental crust, oceanic crust. So it is the edge of the continent. This is our continental margin, but it is an active margin because there is a plate boundary. So this is a different plate than this over here. A passive margin is where our continental crust just slowly shifts into oceanic crust. So there's no margin, there's no boundary. It's all the same plate, but it is still a shift from continental crust to oceanic crust, just all on one plate. That would be called a passive margin. There's not much going on compared to the active margin where you do have that boundary. So what type of continental margin would the west coast of Africa be? What do you think? Take a second to try and guess. Locate the west coast of Africa on this plate boundary map here. And do you think it would be a passive boundary or an active boundary? If you chose passive, you are correct. So let's look at the west coast of Africa here. So here we have continent, here we have ocean, here's the Atlantic. However, we see that this is all the African plate. So it's all the same plate. So we are looking at a continental margin where continent turns into ocean, but there's no boundary there. Nothing much going on, so it would be a passive boundary. So continental margins are made up of a few different components. So continental passive margins, I should say. So you have your continent and you have your continental shelf. So the continental shelf is the continental crust that is still underwater. So sea levels change a little bit through time. So some of that continent will actually be submerged. So the continental shelf is the continental crust, so it's technically still a continent, but it extends past our current day shoreline. So the continental crust that extends underwater, that is our continental shelf, until we get to the edge of the shelf or the shelf break, and then we have a continental slope. So there will be a very steep slope at the edge of the continental slope. There will then be a more gradual area called the continental rise, where there's been some erosion, it's much more smooth. The continental rise, which then leads out to the abyssal plain. So the abyssal plain would be more like the deep ocean. That is where you get to your oceanic crust. So above our continental slope is where we have the transition really from continental crust to oceanic crust. And then we have the continental rise out to the deep ocean of the abyssal plain. So these are just the terms that you're going to want to know when you're talking about continental passive margins. So thinking about that, which letter here do you think marks the edge of the North American continent? A, B, or C? So A is the edge of the coast, our coastline, our present day coastline. So if you wanted to put your toes in the water, you'd want to go to A. If you wanted to study a mid-ocean ridge, you would want to go to C, because this is, of course, our mid-ocean ridge in the middle of the ocean. However, the edge of the continent, the edge of the continental crust, that continental shelf, is there at B. So you can see the lighter blue color of that still pretty shallow water, and then there's a rather steep or very quick drop-off to the deeper water. That is the continental slope, moving out to the continental rise. So the edge of the North American continent is actually way out here at letter B. So you can also see on this, this is the same bathymetry map I showed earlier. You can see really well the outline of the continents. The real continental crust is all outlined by the pale blue, so that almost whitish teal color is showing you the very, very shallow continental shelves underneath the water. Then you can see there's a steep drop-off into the deep ocean, into that deeper blue color also, darker blue color. So after, or next to, I should say, the continental shelf, the continental break, the continental slope, the continental rise, we then have what we call the abyssal plain. So the abyssal plain is sort of the floor of the deep ocean. It can be very, very deep, between like 4,000 and 6,000 meters deep. So this is going to be really the floor of the ocean basin. So it's not flat. It's certainly not flat. There can be hills, undersea mountains. There can be undersea volcanoes or islands caused by volcanoes. But that deep part of the ocean, the deep ocean, is considered the abyssal plain. So you can also see trenches. So trenches are going to be much, much deeper than that abyssal plain. As we know, trenches are the deepest part of our ocean. They are caused by subduction. Trenches can reach almost 10,000 meters deep. So our trench will always be associated by a volcanic island or a continent, if you are looking at continental to oceanic boundaries. But the oceanic trench is always caused by subduction at a convergent boundary. So in this case, we have our oceanic crust and our volcanic island right next door. Excuse me, I meant to say our oceanic trench and our volcanic island right next door. It is, of course, also oceanic crust. And then the last piece of our ocean floor, my favorite, is the mid-ocean ridge. So I know we've talked quite a bit about mid-ocean ridges in this lecture so far, but they are at shallower depths than the deep ocean. So not as deep as the abyssal plain, because the mid-ocean ridge, remember, is an underwater mountain range. So it's an underwater mountain range where we have that divergent boundary. So here we have our plates moving apart. That might also cause some transform boundaries where they rub against each other. But there's always going to be volcanism creating new oceanic crust. So this mantle material is coming up. It will harden into oceanic crust, and then it will move away from the ridge. So in age, the rock will increase in age, the crust will increase in age as it moves and ages away from that mid-ocean ridge. So a fun feature of mid-ocean ridges are hydrothermal vents. So we often see hydrothermal vents along the center of the mid-ocean ridge. So it's essentially an underwater hot spring. So there's a lot of heat being released from this magma chamber. So there can be very, very, very hot water right next to very cold water from all the heat from this magma chamber. So it's very cool because this unbelievable amount of heat is much below the depth that light can penetrate. So there's absolutely no light. There's no sunlight. So any organisms there, the whole ecosystem that survives at the mid-ocean ridge is due to this heat release, is due to these hydrothermal vents, because this region has absolutely no light. No sunlight reaches this area. So there's a huge ecosystem that survives along these mid-ocean ridges just due to the heat and also the nutrients that are released from the mid-ocean ridge. So it's a pretty cool place. So I just want to briefly, for the last part of lecture, go over drawing cross-sections, because this is what you're going to have to do on Tuesday in your lecture. In your discussion. So a cross-section is essentially like a vertical profile along a line on a surface. So imagine you cut a cake, like my cake here, and then you want to see what the cake looks like with depth. So you want to cut into the cake and look at the side of the cake. You want to see a cross-section. So you're looking at the cake from above, you don't know what flavor it is, you don't know what color it is, you don't know how many layers, what kind of frosting's in the middle, is there a filling, is there strawberries, you're dying to know. So you cut into the cake and you look at it from the side. So you can see the layers, you can see that someone, not myself sadly, has this beautiful rainbow cake with all of these different layers of icing in the middle. That is essentially what you can also do with the earth. So you can cut the earth in half, and you can look at the different layers of the earth. So you can see the inner core, the outer core, the mantle, the crust. Here's oceanic crust. Here is continental crust. Don't worry about these labels. These are just layers of the atmosphere. We don't need to focus on that for this class. So you can draw a cross-section of your cake the same way that you can draw a cross-section of the earth. So then what you can do is you can draw a cross-section of some plate boundaries. So my first question here for you is to think about this cartoon here. How many plates are there on this map? So I have this guide here saying that an ocean trench is shown by the red line. So there's two ocean trenches, one here, one here. There's also a mid-ocean ridge. So the mid-ocean ridge is actually in this Y shape. So take a second, try and figure out how many plates are here. So you should have gotten 5. So here's our oceanic trench, which means there's subduction. So this is a convergent boundary. So here's one plate, here's another plate. Here's a mid-ocean ridge, which means it's separating these two plates. So here's plate 3. Here we have another trench, which means there's another set of subduction. So there is plate 4. And then up here, this Y shape, so we actually have our mid-ocean ridge pushing 3 plates apart. So that would be plate 5. So when I'm doing something like this, I often find it very helpful to actually draw or actually denote where the boundaries are. I would say, okay, here's one boundary, here's a Y-shaped boundary, and here's another boundary, so that I can see visibly on the page. I've sort of already outlined the plates, and it's really easy to count. This was a pretty tricky example, I'm not going to lie. So if you mastered that one, you're in great shape. If not, I hope the explanation and the numbering helped. So the answer should be 5, D5. So I had some volcanoes. I'm just going to speed through this because I know this has been a long video, but it's so much fun. I love plate tectonics. Some volcanoes were marked here, but we know that we would also find volcanoes all along our mid-ocean ridge because the mid-ocean ridge is that spreading center. They're going to be all underwater, but we do have that creation of new oceanic crust. There is volcanoes all along that region. And then the same on this continent. So this is a trench, which means that this spreading center is pushing this plate away from the mid-ocean ridge towards this continent. So since this is a trench, we know that this oceanic crust must be subducting down underneath the continent, creating volcanoes on that overriding plate. So a way to keep straight everything that I just said is to draw the cross-section. So instead of trying to explain just looking at from above, you can actually draw out the cross-section. So imagine you took your knife, your cake knife, and you cut along from X to Y, and then you looked vertically. So you looked at the layers of the cake, you looked at the layers of the earth, and tried to draw it out here. So I'll show you what I drew. It's a little hard to draw on digital format, I won't lie to you, I'm not great at it. But what we would see is we have our, so we're walking from X to Y. Oops. So from X to Y would be walking here from X to Y. First, you would be on your continent. You'd be walking on your continent. You know that you have volcanoes here. You have volcanic mountains, so you would have higher higher surfaces. And then eventually you would hit the coastline, and you would hopefully have your scuba gear on so that you can continue walking on the surface of the earth underwater until you get to a very, very, very deep trench, which is outlined by the red line. So here we have our deep trench. You know then that you're walking on oceanic crust, so this would all be oceanic crust until you get to your mid-ocean ridge. So this is an underwater mountain range, so that's why you see the height go up. Here's our underwater mountain range. And then you keep walking on your oceanic crust till you get to another trench, so another very, very, very deep area. And then you hit your other volcanoes, so then your your elevation would start to go up until you hit your volcanic islands. So that would be the surface. So if you removed the water, looking at the surface. Underneath that is where the details come into play. So notice in this drawing that the continental crust here is drawn much thicker than the oceanic crust here. So we have our very thin oceanic crust. Here's our subduction zone where it's drawn so that our asthenosphere mantle material is what could be rising up, creating new oceanic crust. So at this mid-ocean ridge, we have our boundaries moving apart, the divergent boundary here moving apart, which means that this oceanic crust on both sides is going to be subducting underneath the continental crust. So in both situations, the oceanic crust is subducting underneath this continental crust, which means around here is where you'd have your melting, rising up, creating this mountain. So we have our layers being the oceanic crust, the lithosphere, and then the asthenosphere. So here we have our much thicker continental crust, our lithosphere, and then the asthenosphere would be down here. It just didn't fit on the drawing. So this would be what I'm looking for when I ask for a cross-section of a drawing like this. This one is particularly difficult because there are so many different combinations of things going on. You're going to get a lot of practice with drawing these on Tuesday. I just wanted to really go over how you approach something like this because I realized that no one knew that they were signing up for such an artistic class when they said they would take oceanography. So here is just one more example. Here we have a trench, this dashed line. The trench is next to a volcanic island chain here, and then the mid-ocean ridge. So the mid-ocean ridge is offset, remember, by little transform boundaries, but our cross-section is going from X to Y. It's going to cross right through that mid-ocean ridge. So if you were to draw it, we would see our continental crust, and you'll notice that this is very shallow because this is still our continental crust. So this is still quite shallow before we get to the continental rise and more the abyssal plain out here. So we have our very shallow continental crust before it drops off around here. And we then have our oceanic crust, which is much thinner than our continental crust. We will then hit this chain of islands. So we have this chain of islands. The surface is going to go up above our sea level. And then we hit a trench. So you see our trench. And then you would, there's more ocean here, oceanic crust, before you hit the mid-ocean ridge. So I always start these drawings by drawing the surface. So sort of like as I've been explaining, if I was to walk from X to Y, and I didn't have to think about breathing underwater, what would my walk look like? Where would I be going uphill? Where would I be going downhill? Where would I be moving a rather flat surface? So that's always how I start it. And then I start to think about, okay, what are the boundaries? So how are things moving? This is a mid-ocean ridge. Oh, that's why I have that small mountain range. And then you can draw in the different layers. Make sure the asthenosphere is able to come up, release that new that new oceanic crust. And we know we have our trench with our mountain range. So this oceanic crust must be subducting underneath. So here we have our trench, and then to the west, as that oceanic crust is subducting, we would have melting rising up to create this mountain chain here. Then we have more oceanic crust until we hit the continent. So I hope this gives you some good examples of what I mean by drawing cross sections. You will be able to do that on Tuesday in discussion, so you'll be able to do it as a group. You can also refer back to these figures because they might be something similar to what you see in your discussion section. So that is all for now. Next week we will talk more about water, salinity, density of water, and then ocean circulation. So surface circulation, deep ocean circulation, and currents, how water actually moves. So hope you guys enjoyed it, and I hope you have a great weekend.